So from our special case in the last example, if we have that f of x is equal to x minus c times some quotient function q of x plus r, if we have that the remainder is equal to 0, then what's going to end up happening here is that f of x is equal to x minus c times q of x. That is, if the remainder is 0, then we have that x minus c is a factor of f. And that's what we call the factor theorem, that f of c being equal to 0 is actually equivalent to x minus c being a factor. That actually goes in both directions. Those refer to the same thing, just in opposite ways. They're kind of inverses of each other in terms of logic. So let's finish this section here with one quick example for how this works, how this can be used. For this example, we want to solve 15x cubed plus 14x squared minus 3x minus 2 equals 0 using the factor theorem, given that f of negative 1 equals 0 for the function f of x defined in the same way. So what we want to do here is see that because f of negative 1 equals 0, that is a factor, and then split it up. But knowing that it's a factor doesn't really help us. Knowing that x plus 1 factors out, it's good, but we don't know how it factors off the top of our head. It takes a little bit more to do that. So what we're going to do is use synthetic division to get the factored form that we should expect here, and then solve from there. We're going to have a quadratic, and we know how to solve quadratics. You can use the cubic formula, but generally you don't, because cubics are not fun to deal with in that way. So we're going to have, I'm going to skip a half step here, 15, 14, negative 3, and negative 2 for our coefficients, 15x cubed, 14x squared, negative 3x, and 2. And then over here, we're going to divide this by x plus 1 because we're assuming that x plus 1 is a factor based on the fact that f of negative 1 equals 0. So we've got a negative 1 that we're going to be chasing out here. Pull down the 15, multiply the negative 1 by 15, you get negative 15, which means you'll be left with a negative 1. Pull over the negative 1, pull that up there, we'll have 1. Take negative 3 plus negative 1, you get negative 2, multiply negative 2 times negative 1, you get 2, add those two together, and you get 0. A little bit quick, but that is how synthetic division works. Like I said, once you get used to it, it's a lot faster, it's a lot more compact, it's just better, really, than polynomial long division once you understand how you're moving the pieces a little bit carefully. In any case, that tells us our factored form here is going to be f of x equals x plus 1 times 15x squared minus x minus 2 along with 0 for the remainder because it is a factor. And this might not be the very cleanest thing to see how it factors, but it actually does. We have factors for 15 are 3 and 5. Negative 2 are 2 and negative 1. So what we'll end up with here, with some careful algebra, is x plus 1 times 3x plus 1 times 5x minus 2, which says that if we want our solution set, we want to find the places where this whole thing is equal to 0. By the zero product principle, that will be the set of values x equals negative 1, which we should have been able to get from the start because it told us, along with the things that happen for this to be 0, which is x is equal to negative 1/3, and the things that this needs to happen to x in order for it to be 0, which would just happen when x is equal to 2/5. So technically speaking, we didn't really use the factor theorem here, but it did help give us a hint as to where to look. That because we had that f of negative 1 is equal to 0, we should have been able to suspect that we'd get a nice thing by dividing it out, and in this case we did. And once we got there, break it down to further parts because that quadratic was pliable, let's say, factorable, if you're being a little bit more specific, and we got our zeros. Where this is about as nice as it gets, because a lot of things, no matter how nice they look, don't actually factor. It's honestly very rare that we get findable zeros without getting really creative, much less factorable zeros, or at least nicely factorable ones. And what we're going to talk about in our next section in 3.4 is how we work when we don't have such manageable pieces in terms of things like the rational root theorem, Descartes' rule of signs, and other methods that we have for avoiding unfactorable things.